let's talk about the first component. It's finite fields. So the idea is next. Here we have a finite field over prime number. What does it mean? So we have in our possession a set of numbers from 0 to 22, where we actually can conduct operations. And the main idea is that we can apply here operations like addition and multiplication, but all of them will be, the results for each operation should be also divided by modulo 23. What does it mean for us? So every time when we are conducting operation, and in case if there is overflow, the result will be always in the same set. So here we have an animation for addition, multiplication, and this is an example how can we find negative values for over finite field. So for example, if I want to have -1 on this scale, I would need to go into this direction and I will end up here. So for example, if negative -1 will be 22, -2 will be 21, and so on. So basically the idea is that you need to find a right number in finite field just to conduct this subtraction, for example. So for multiplication or division, we would need to find an inverse operand, which should be, let me just pause it for a second. So the idea is next, we need to find an element which is inverse in the group. Let's assume I want to divide 5 by 20. So in order to find the element, inverse at element to 20, I would need to find another number, which I need to multiply and apply modulo operation, and in the end I will get 1, which is identity element. And basically in our case, the inverse to 20 will be 15. So if I want to divide 5 by 20, I would need to multiply it, 5 multiplied by 15, and basically I will get some results. Okay, now about some properties. Why are we using finite fields? First of all, we are trying to avoid overflows in our operations, meaning if there is something which goes out of the field, we would apply modulo operation and we will go back to, result will go back into the scale from 0 to prime number. Also, we don't want to, we want to get rid of fractions in general. So we want to operate with whole numbers. And one of the properties, which is a really awesome one, discrete logarithm problem, which basically says that it's hard to reverse engineer parameters that were used for some operation. For example, if I will give you number 6 and say that this number was conducted from multiplication of two numbers, you can easily come up what was the values used for. Even if I will give you an extremely huge number, you still can be able to do this by writing some small program which will do some brute forcing and try to find these operands. But if you will apply a modulo operation in the end, your basically result will be somewhere like readjusted back to the finite field, and it will be hard to figure out what was the original values used for the operation. So that's basically one of the reasons why we are using finite fields in zero knowledge proofs. Second one is polynomials. Polynomial is basically a function with one variable. So the idea is next, that if you will take a polynomial and provide it with some value, in the end you will get a result. And for very specific polynomials, they can be located like somewhere like on the line here or on this curve. So no matter how many data points are you going to use, for example, I have 1,000,000 points. So I can express them with this short equation, which is basically an efficient way to provide or commit to some data. I mean, I don't know, something like it's efficient way to represent the data in a short manner. So here we have an example how can we actually generate data based on the function, but the question is, can we do opposite way? For example, I have an arbitrary data, and can I convert it back into polynomial? So we can try to do something like, let's try to encode a hello world message, for example, or string. So for that, first we need to find a right finite field, which so we know that, for example, so to represent one character in computer, we are using 1 byte, and 1 byte can encode up to 256 combinations from a ASCII table. So the closest prime number will be 257, and eventually we will be using this prime field for our polynomial encoding. So after this, we can go directly to ASCII table and find ASCII codes for each letter. So we have ASCII code for letter H, E, L, and remaining parts. And after this, when we have these numbers, we can actually construct a polynomial. So for that, we would need to use something which is called like Lagrange interpolation method. I'm not going to talk about this one, but the idea is that in the end, we will get something like this, which looks a bit scary. But if we will try to evaluate this polynomial, for example, for x equals 0, all of these terms will be cancelled out, and we will have only 104. And basically, it's ASCII code of letter H. If we will evaluate polynomial at x equals 1, we would get ASCII code for E, and if we will continue to evaluate it for E, and we will continue to evaluate for all of the letters, we basically will get ASCII code. So this is kind of like a way how you can actually encode the data. Also, we can plot it, and we will see that it's something like this. Each point is basically a letter from the message. And also we have a short example in Python how it works. We have a polynomial. We are trying to evaluate it over x equals 0, and we will get ASCII code for a letter H, and for us as well. So you can think of polynomial as something like mass equivalent of array or map data structure, where you can use either index or k to get your value. Okay, so why are we using polynomials? So we can use them for data recovery. So let's assume I want to send this hello world message over the network, and so we know that network is kind of like messy environment, and we can lose some packets can be lost. And the question is, how can we actually reconstruct the data without asking the sender to resend the data again? So here we have our polynomial, and also we have evaluation of this polynomial for all of the letters. So now we want to extend this message with additional evaluations. So as a result, so we are trying to evaluate polynomial over x equals 11 and up to 14. And basically we will get these ASCII codes. Some of them are printable, some of them are not, but eventually we have this extended message. So now we are sending it over the network, and the recipient receives this. So, oh, I forgot to mention, so this extension up to 4 elements says that we are allowed to lose up to 4 packets from the message, and we can actually reconstruct the data back. So here we have a loss at packet number 2, 7, 8, and 14. So what we can do, so we can actually use again a Lagrange interpolation to reconstruct the polynomial and evaluate it over the missing packets. So here is an example how it works in principles with Python example. So we have an order of each packet. We have also the values, and now using Lagrange interpolation, we are getting these values back by having the polynomial, and now we are evaluating for the missing packets. Okay, yeah, so basically this is an idea. And this is what is called Reed-Solomon codes. This is the main principle how it works. And you can see this thing applied, for example, in QR codes, when you're trying to read the code, QR code. Also, when you are using, let's say, a scratched Blu-ray disc, it will also has kind of like this principles used to reconstruct the data. Okay, what else we can do with polynomials? Let's talk about commitment schemes. So let's say I want to build a game on a blockchain where multiple people should pick a number, and the closest one to the target will win, for example. So the easiest way to implement it is to use a hash commit reveal scheme, which look like this. We have a data which we want to commit to, and for that we would need to use to generate a hash. And this hash first needs to be sent to recipient, and when there is a time to reveal the data, we will send the data to the recipient, and basically recipient would need to recalculate the hash and check it against the original one. So this scheme is trivial and easy to understand, but basically it has a couple of downsides. One of them is that the same operation is conducted twice. So we need to use hash function twice for the prover and for the sender and for the recipient. Also, if you are going to send it over the network, for small messages, it's going to work. But the problem is, what if I want to commit to something which is like 2 gigabytes in size? We can send the hash, but there will be some problems to sending this data over the network. I mean, like, it can be some connection issues and things like this, or it will take too much time just to deliver the data. So it's basically not going to happen. And for example, if you want to build this commitment scheme for big files, for example, on Ethereum, it's not going to happen because of the gas fees. And actually there is a limit in amount of data that can be consumed in one block. So what we can do, we can use polynomial commitment schemes. So here we have on this side, we have kind of like a prover or a committer. On that side, we will have a verifier or a recipient, and this will be something like a communication channel in between. So now we have the same data, but instead of operating directly with the data, we would convert it into polynomial first. And next, we would need to commit to this data by using polynomial evaluation over some random point. So we are picking random point t, and we are evaluating polynomial over it and send these two values to the recipient. So now recipient says, now it's my turn to pick the value, and I'm sending it back to you. Please evaluate the same polynomial with this value. So prover will do this. And yeah, one thing I forgot to mention is that when you are working with polynomials instead of data, you will automatically acquire some additional properties based on which you can actually build these commitment schemes. So the next step here will be constructing another polynomial. I'm not going to talk about why we are using this, but eventually we are able to construct another polynomial from this data and evaluate it over this value t again and send it back to the prover. And actually, based on those 5 parameters, we can actually verify whether the commitment to the data is correct or not. So this is an efficient way how to commit to some data over the network, and we are providing only 5 elements. I mean, like, no matter how big the data is, it should be enough for us just to use those 5 parameters. Also, this is an interactive scheme, meaning that prover and verifier are going kind of like back and forth, communicating just to get the right results. But we can convert it into non-interactive by applying another techniques. But the idea is that actually this step number 2 will be, the arrow will be flipped into that direction, and the prover is required to generate all of these values on his side and send them at once to the verifier. Yeah, and the last thing is about privacy, I guess. So we can see that from this commitment scheme, verifier learns a little about the general statement or the data from the prover, because we are only sending like two evaluations which are related to the data itself. But if you want to have kind of like complete zero knowledgeness of this commitment scheme, we would need to apply here elliptic curve cryptography, so which we are going to talk next. Yeah, so elliptic curves, basically it's kind of like an equation which also is kind of like a polynomial maybe. But the idea is that using this thing, we can actually build all of our kind of like cryptography around zero knowledge proofs, and I mean, like, and all the blockchain is basically built on elliptic curves. This is a visual representation of elliptic curve. So basically everything that is happening in blockchain, like signing transactions, verifying transactions, generating public keys, are happening on this curve. I mean, your public key somewhere like on this curve as a point represented here. So as I said before, each mass construction has a set of operations, and for us it's important to have kind of like addition and multiplication for this. So here we have an example how point addition works on elliptic curves. So it's not like we have it with numbers. So here we have an idea. In general, we have kind of like 2 points that we need to add. Visual representation is something like this. You need to draw a straight line through those 2 points, and at the intersection of with the elliptic curve, you will get a negative result of this addition, and you need to flip y coordinate, and it will be your final result, which is kind of like a new point on a curve. And this principle is applied across all the points on elliptic curve. So, okay, now a bit more about addition. So sometimes it's called scalar multiplication, which so each elliptic curve comes with a point which is called G, or generator point. The idea is next. So using this point, we can actually generate all other points on the elliptic curve. So to do this, we would need to take G, add it to itself basically, and we will get something like 2G. And here, here 2 is kind of like a scalar. That's why we have the scalar multiplication name for this operation. So if you want to continue, we will use G again, and now we will add it to 2G, and we can continue this all and over again. Now let's take an example. For example, a private key. Yeah, your private key is basically a huge number. So what you can do with it? It's also a scalar. If you will multiply it by generator point, you will get your public key. So, and basically it's kind of like a rule that you only need to provide your public key to the audience, and private key should be kept somewhere safe. So what does it mean? So that we actually can hide original values by points using this scalar multiplication. Also, we can hide computations using points, meaning that, for example, I'm conducting some sophisticated operations. I can represent them as operations in using elliptic curves. For example, this one. So I want to check whether these two numbers are added by first we need to hide them under the elliptic curve points behind them. So first we are hiding number 6 into elliptic curve. We have it. The next one we will hide 2 behind elliptic curve point. Now number 4, and we can, after this, add those 2 points together. And finally, we can check whether this value equals to this one, just by comparing points. Okay, and basically, if you will do the same operations but over elliptic curve points, it means that we can do the same operations but without revealing the information to others.
Yeah, so that multiplication by the generator, that's not just a simple multiplication, right? Because then you would be able to reverse to get the private.
Yeah, basically everything happens in finite field.
Okay.
So what does it mean? That each time when we have some kind of like result, it should be kind of like readjusted back to the same finite field.
The generator would be larger than the field, right? Or the key would be larger than
the key. No. Key is basically a point. So we are there is kind of like 2 ways how you provide your public key. It's basically either kind of like extended version, which contains x and y coordinate, but usually you can provide the shorter version, which is only just x coordinate, because from x you can easily find where is y coordinate here. Okay, so now we can go back to our original commitment scheme and replace all evaluations with points, and we will have something like this. So now the data is completely hidden from the verifier, but we still not able to finish this this commitment scheme to convert it completely to points, because we have this equation which requires to have a multiplication. And for that, we would need to address how multiplication, point-to-point multiplication works in elliptic curves. Actually, there is no such thing as point-to-point multiplication. And basically, instead of this, we can use an additional thing which is called pairing. The idea is it's kind of like equivalent of multiplication, but in another way. So there is a couple of elliptic curves available and are able to provide pairing. So idea is next that you need to, if you want to pair 2 points from you would need to take for each point from different elliptic curve, and by applying pairing, your result will be landing into completely different group, which is not elliptic curve. It's kind of like a finite field. And so now we can try to finish our equation here. So first we are replacing our evaluation with elliptic curve points. So we have evaluation over Q, T is elliptic curve point, P is also evaluation. So we still not able to finish this, conduct these operations, because R is a scalar and evaluation of P over R is also a scalar. So what we need to do is basically to convert them into points, and to do it by basically just multiplying them to generator point. But first we need to define which point it belongs to which curve. So first we have kind of like this, this point belongs to this curve, that point belongs to this curve, and the remaining part is this. And so after this we can convert scalars into points, and we will have our final equation which will work basically. So that's an idea how actually one of the protocols in zero knowledge proof are working. For example, Plonkish protocols are using this technique to verify proofs. Yeah, and that's basically all. Thank you. Any questions?
Can you tell us some application in real life to zero knowledge in general?
So I mentioned one of them is basically to generate a proof for Ethereum block generation. So there is a couple of works which are doing, I mean, like trying to people to build this proving schemes. So the problem is that currently to generate a proof for Ethereum block can take up to 2 hours. But basically, if you will be able to keep up with the phase at which blocks are producing, we can replace consensus mechanism by verifying just proofs instead of like re-executing the block.
Okay, so if we do that, we will. What will be the benefit? It will be more light to do, more fast to do transaction in general.
Yeah, actually, I mean, like it's easy just to send a proof over the network, then kind of like send big block and wait when the all nodes kind of like have the same kind of like height of the block and can verify on some results.
You could have very, very light clients like on your phone. If you just have to verify a proof, it's very easy to do that rather than re-executing the whole block. So if you wanted like light clients on your phone and you abstracted away the EVM into just a proof verification, that's one of the things. Also, another like real life thing, a little bit ago, we actually had somebody working with the BC government on identification. And they built an application where you could essentially like prove things about your ID. So you could prove, hey, I'm 19 or over 19. You can sell me alcohol, but I'm not going to show you my ID, show you how old I am or anything like that. And yeah, there's a bunch of other applications out there as well. But yeah.
So yeah, so in terms of zero knowledge, there is 2 applications, is like privacy, and one is like making lighter the proof.
Yeah, exactly. Like privacy and succinctness. So like, yeah, faster to verify than having to re-execute.
Yeah, but both are not linked. I mean, you can use, for example, privacy without using zero knowledge for proving, and vice versa. Or
I mean, not all of the things. Like ZK provides a lot of those that you wouldn't be able to have without ZK. Yeah. Like privacy applications, you cannot necessarily build them without zero knowledge.
Yeah.
That's also true.
So for example, you can take any kind
Zero is an optional property of
and
knowledge proof.
sometimes it's, I mean, currently it's not very popular. I mean, like everybody's just trying to generate proofs about some execution like rollups, for example, and there is no notion of privacy. But if you want to actually to build it, you would probably need to think about some, I mean, like real case scenarios here.
Yeah.
For the blockchain.
And then yeah, like you were saying, if you don't want the speed, like there's ZK Snarks and ZK Starks all have that succinctness, but there are other ZK protocols as well that don't have like a succinct properties, but probably not like very like you wouldn't necessarily want to use those. I guess I don't know. Depends on your application, I guess. But
Proof of proof. Make people do arbitrary computation. I'm kidding. I really like the animations.
yeah, I was actually gonna say that. How
Yeah.
did you record and make a lot of those animations? The slides were awesome.
Actually, all of these are videos. I mean,
Okay. Yeah.
yeah, it's kind of like short clip, which is looped.
Cool.
Yeah, I've never seen it visualized like that. Like the finite field helped me wrap my head around it.
And the hello world, like sending it over a network example is great. I never really thought of it like CK proofs where you're reconstructing the polynomial like that. I never thought about it in that way. And that was pretty helpful, I think.
Which one? The last one? Mm,
Oh, the finite fields. Elliptic curve.
mm, this one? Okay.
That was very fun to watch.
Ah, yeah.
So is that a valid elliptic curve when they
That was exactly what I was gonna ask.
detach?
Yeah. Actually,
When it-
they are
when it buds
basically
off.
based on these parameters, properties may change and security properties as well. So not all of the elliptic curves are safe.
Yeah. Don't use the Fed curve.
For this, I would say that you should kind of refer what cryptographers are saying, because they're kind of like more familiar how actually to do the right attacks on these constructions. Yeah, just stick to the professionals, I would say.
Probably picking you know, the same ones every time when you're generating keys.
Could you go to the generator slide? Like where you had G and then G times 2. So you said that you could reconstruct this curve using just G. Do you need other like parameters of the curve, or
Again,
I may have understood it wrong, but I thought you had said that you could like generate this curve using just G, like the
yeah.
generator.
Yeah, so basically, by using only generator, you can reconstruct all the points that are located on this curve.
Oh, okay. Cool. Any other questions? All right, thank you so much. One more round of applause. That was awesome. Thank you guys for coming by. We can keep chatting a bit, but there's also a POAP at the back, a little NFT type thing that says you were here, and it's got a nice image on it. Just on the black poster beside the rug there on the wall. You can tap your phone against it and grab the NFT. Yeah, just housekeeping. A few of us are heading out to Asia for the next couple of weeks, but I believe there will still be some people here to kind of handle stuff. So yeah, hopefully we'll see you next week or in the following weeks. We do this every week, and yeah, thanks.